Okay, let's start. Before I proceed to my second lecture, I'd like to ask whether my teaching material for the first week is too difficult. If it's too difficult, hand up. It's about looks. I'm glad you you don't find it's too difficult, right? Look, look. I have to admit it's not easy. Uh, but I already said the everything is about numerical linear algebra. That's why our first year mathematical courses we must learn 1 year linear numerical linear algebra. Okay, so for some universities they teach abstract algebra, linear algebra, which I well topology, rings, and such a concept are I don't find is too relevant to numerically to what we are doing here. So if I were in charge of developing syllabus for first year mathematical courses, I would devote more time to numerical linear algebra rather than abstract linear algebra. So I know the usually second semester of linear algebra is about abstract algebra. Anyway, so that's my purpose. I only use numerical linear algebra. At most, you will see eigenvalues, eigenvectors. And you see such simple stuff can lead to a significant development in softwares, in algorithms. At any time, if you feel my teaching material is too difficult, let me know because I may spend more time on it or I may reduce some complexity in it. The purpose for me is that I want to give you the best proof and the best evidence why the algorithms that I lecture here is correct. Today, I'm going to talk about probably the most important algorithm used in machine learning, the accelerated gradient method. Okay, nowadays people use accelerated version, not the gradient itself. Even for the stochastic gradient method, we will see next week, and we will add some momentum. And people may ask why. I will talk about a little bit history at the end of this lecture rather than at the beginning of the lecture. That's a funny story behind this great method. So previously, we want to solve this problem. Remember, this fx is abstract, all right? I didn't give you the structure, but you see the lasso linear regression or logistic regression. I believe everybody knows the two regressions: linear regression, logistic regression. This fx is consists of many components, and how many data point you have, how many components there, because it's a loss function. Okay, so we have a function f. We assume f is continuously differentiable. Okay, continuously differentiable. You think about logistic regression. Okay, it is differentiable as many times as you want. All right, it's a very good function, and usually we have very nice functions even for deep neural network. You take up the activation function. The other functions are linear, component of linear functions. And the linear function, we know they are differentiable as many times as you want. It's just the derivative is 0, all right? Higher the order than 1, okay? So you say we deal with functions that are continually differentiable, well-behaved, aided by something a little bit strange, little bit difficult. For example, for us, Lasso. Okay, I like Lasso because this problem is so simple. It's not that simple, and it has a solid statistical theory behind it. So you see, quadratic function, okay, nothing better than quadratic function, okay? You add L1 norm, absolute value function, all right? This one is difficult, right? But it's not that too difficult. We will see how we deal with this term. So previously, we have this nice function. We want to use gradient method. How do we use gradient method? We calculate the gradient, that is the negative gradient. We all know that in our calculus, gradient meaning if you follow gradient direction, your function value increase, okay? That is Taylor expansion is all about, okay? If you follow the negative, you put a minus before it, you follow the negative gradient, that means you decrease your function value, okay? And that is very natural, okay, for us. Whenever we want to, increase your profit or you reduce your cost, and you need to know what is the derivative of my objective, all right? If you know the derivative of your objective, you simply follow the negative direction, so that is a minus, okay? So the point is how far you follow that direction. So this vector is a direction. Remember, in high school days, we know vector is an arrow, right? You follow, this is the current point. You stand here. So this is my negative gradient direction. I go along that direction. So xk plus something. So how far you go, that is alpha k. That is something puzzles many people, okay? How far you go. So in one of my lectures, I will devote the whole lecture about the alpha k, okay? So I tell you what kind of alpha k you should use, what strategies are available there, and software companies, implementation, all about such things, okay? So we leave this out, okay? At the moment, we use constant 1 over k, right? 1 over L. We use constant step size. And we know that we considered two classes of function. One is L ellipsis. L ellipsis is a function values does not increase too fast in terms of the change of the variables. So L smooth is the gradient does not change too fast. Okay, they're all ellipses. Okay, so with the L ellipses, and this is the complexity is 1 over square root k. All right, this is accuracy. So for the L smooth function, so this smooth function is better. Okay, you think about quadratic function. So it's 1 over k. Today, I'm going to introduce accelerated variant of the gradient method that give you 1 over k squared, okay? So that means if you use 10, previously you use 100 iterations, now, today, you use only 10, all right? Okay, it's 10, it's k squared. And if I use today's algorithm, I use 100 steps, okay? My first lecture's algorithm, they use at least 10,000 iterations. You can see the speed acceleration is very fast. That is why people like it. People use it, okay? So more than that, it can deal with Lasso, all right? not only have we learned the accelerated gradient method, but also we can deal with something like this. Okay, you can add a little bit no annoying term. Okay, so that is my title. My today's title says proximal. Okay, so if you look up in your dictionary, what is the proximal? Proximal meaning nearby. Okay, very close. Okay. Okay. Anyway, so let's get to the technical part. Okay. So this is my general framework. Okay, setup. I want to minimize a function that is a capital Fx. Okay, that is I use a capital Fx. Capital Fx. I have two terms, f plus g. Okay, you always remember my function has two terms. The first term f is a nice function, as nice as you want. Okay, you can put all the best properties to f. Okay, doesn't matter why. Remember Lasso. Lasso is the quadratic function. Look, a quadratic function has anything you want. All right, it's so simple. All right, so but g function. Okay, you think about it, it's absolute value function. All right, I like to deal with such a structure. Okay, so of course I like my function g to be convex. Okay, convex. So I'm dealing with convex optimization. So all my functions are convex. All right. Last week we talked about the convex function. All right, convex function. Why convex function is good? Because convex function, any gradient, the gradient equals 0. That gradient equals 0. That point is your global solution. All right. So you only need to care about the gradient. Okay. If gradient is not 0, you use gradient method to decrease your function. As soon as it reaches the gradient being 0, you get your solution. But if function is not convex, it's different. Think about the cubic function. All right, cubic function, x equals 0. 0 is not the minimal point. Okay, so you think about it, you can visualize the cubic function, x cubic. All right, it's different. X cubic is not convex. Okay. Now, that is my key. I just give you one result, one proof today. Okay, one result is that 1 over k complexity. All right, one proof. But behind the one result, one proof, we need a lot of preparation. Otherwise, other people would get famous. Okay, you need something magical. Okay. All right. So what I need? I need three things. One, strongly convex function. So previously I introduced convex function. Now I need a slightly stronger concept called strongly convex. So the definition is really very simple. Then next one, I'm going to need a proximal operator. So that is a fancy name. I will show you. We see it every day. Okay, proximal operator. So lastly, that is the acceleration scheme. That is the magical part. That is not anybody can handle it. All right. Still nowadays, people still puzzled how the acceleration scheme was initially proposed. People use different, I saw papers, people use different mechanism, different strategies, framework to understand the original paper. All right? As you will see, that part is a bit magical, okay? Look, so that is my, the first tool. I need strongly convex. So I have a parameter called mu. You think about quadratic function x squared, okay? X squared, that mu equals 1, all right? So the function, if you take away a quadratic function, okay? If you take away a quadratic function with coefficient mu over 2, if this function still convex, and the f function is called mu strongly convex. Think about you think about this you think about this quadratic function, all right? So this is my fx, okay? This is the quadratic function. If the quadratic function fx take away 1 over x squared, you see they cancel each other equals 0. Of course, function 0 is convex, all right? You can test, you can check the definition of the convex function. 0 function, look, this means for any x, the difference is 0. All right? According to our definition, this mu equals 1. So that means fx is 1 strongly convex. Okay? You see, there are a lot of strongly convex functions. The square function, this one, is one of the strongly convex function. If you so you say I always use this quadratic function. Why use this quadratic function? Think about Pythagoras theorem. 3 squared plus 4 squared equals 5 squared. They are all quadratic functions. Okay, so you can see that's cosine theta squared plus sine theta squared equals 1. That's Pythagoras theorem. So that is why quadratic function is so important. It appears everywhere. Okay, so it has a so if you want to understand the strongly convex function, you just think about x squared. Okay, any property that x squared has, and other strongly convex function also have. But the point is, yes, you have so many strongly convex functions. So what is good about the quadratic strongly convex functions? Strongly convex function has this very good property. What is the property? The property is this. The function can be bounded below by a quadratic function. Look, f is strongly convex. I don't know this function. Assume I don't know. I just know it is a convex function. It's a strongly convex function. Okay? And we can use a quadratic function. Look, this is right-hand side. Remember, so don't be afraid of this such a representation. It is a quadratic function. Remember, dot product. All right? Dot product. So this is dot product. This is the function value. This is the quadratic term. Okay, this is a quadratic function. That means your function can be bounded from below by a nice quadratic function. That means your function is bounded by a function like this, like x squared. Okay, think about it. You have a nice curve. That curve is bounded by a quadratic function. You would be happy because anyway, the bottom line is that I got a quadratic function to support me. Okay, so and the simplification of this one give you what I call the quadratic growth. What is quadratic growth? Suppose you have this function. Suppose this function you have an optimal value that is x star equals 0. Okay, away from 0, this is the optimum value. You grow quadratically. Okay, your function value grow quadratically using this function. Okay, using this as an example. All right, so this one. So this is my quadratic function. This is a 1 strongly convex. This is 0. This is my objective function, the minimum value, the optimal value. You think about any point, this x, okay? Pick any point, this fx, take away fx star. So the function value from the optimal value, okay, greater than or equal half x squared. You see, and this term really is this. Okay, it's just the x star is 0. Okay, so that means if you move away from optimal value, your function value grew very fast. Okay, quadratically, you grow fast. You think about you want to find your, or you find your, for example, in future, you are manager of a company, you want to reduce your cost. And you model your cost as a quadratic, as a convex function. You found the minimal value, and you don't want to shift it away from the minimal value, because once you shift away from the minimal value, it grows very fast, quadratically. That is what I call quadratic growth. Okay, so this is such a growth. Applies to strongly convex function. All right. Okay. So what is the proof? The proof is, look, the result looks very, difficult, very complex. Okay. But look at the proof. The proof is this. So because this fx is strongly convex, according to the definition, you take away this part, is convex. And then you use the convex function. Remember, the tangent line always below the function itself. So this is a tangent line. Remember, this is a tangent line. Remember, look, that's why, once again, that's a linear algebra. Okay, so this is a function is above it. So, but you can calculate the gradient of h. Okay. Then you substitute to it, you get your result. All right. So that is how you get it. And because of this quadratic growth property, you know, for strongly convex function, there's only one solution. Okay. Only one the minimal point. Think about this function. There's only one minimal point. You cannot find the second one. All right? That is the benefit of strongly convex function. Okay? But for convex function only, you may have many minimal point. Think about the function 0. Everywhere is the minimal point. Okay? Function 0 is convex. Okay? So this is what we want to use. If f is both L smooth and mu strongly convex, this function can be bounded below by a quadratic function and can be bounded above a quadratic function. So what it says is this. If my function, for example, is like this, this is a strongly convex, then what I can say is this. Give me any point. Give me any. You pick any point. I can do this. I can draw a this is a quadratic function. Okay. I can construct a quadratic function and another quadratic function. Okay. So this is another quadratic function. So I can give me any point. I can draw two quadratic functions. One is above the function itself. This is my fx. And another is below. both functions are quadratic. Remember, you have to appreciate the difference between quadratic function and functions. Okay, quadratic function is something we know very well. Okay, remember that is when we learn mathematics, when we learn anything, people find, okay, why is it so complicated? You think about this. It's all built on what we are familiar with. Okay, you can think any of your courses. It's all built on what we have familiar with. And remember, I always mention quadratic function. Quadratic function is the motivation behind many development. All right. We first learn quadratic functions and we know it well. Then whenever we have something new, we always want to say, okay, whether I can use a quadratic function to understand this unknown thing. Okay, if you apply such methodology to your study, you suddenly feel that, oh, this is not that difficult. All right, the courses is not difficult. All right, so you say this is you might say some people say sandwich theorem is in between. All right, so the point is that I can construct two quadratic functions that that can approximate this quadratic function. So this is the first thing, strongly convex. The second tool is called proximal operator. All right, the proximal operator. So what is the proximal operator? So I think that I use this whiteboard is you cannot see from the far behind if I use this part. So the point is what is the proximal operator? I said the proximal operator is a nearby point. Assume, all right? Okay, probably I will draw another graph there, okay? Suppose this is my region, okay? This is my region C, okay? So this region is open to the right, okay? I don't know, this is, there are a lot of main points. Suppose I have this point here, X, okay? I get a point. So many times, many situations, you want to find the nearest point. This is the nearest point. Okay, from the region C, okay? All right. We all know geometrically, this is this. Okay, if you draw the tangent line, this is a 90 degree. So what is this? This is a projection. Okay, you always want to project a point to the region. Okay, so you want to find the closest point to this region. Okay, this is the new point. You want to find the nearest point. So the nearest neighborhood. All right. Of course, this I would say nearest. This involve a metric. All right. How do you measure how far? All right. Usually we use Euclidean distance. Right. From Hong Kong to Beijing, we always use flight path. That is the flight. You know, airplane always take a straight line. So that is a Euclidean distance. But sometimes that distance does not reflect reality. For example, if we drive from Hong Kong to Beijing, you would use a road. The road is zigzagging, right? That road distance is also a distance, okay? So that is why you see in our, probably you learned data mining, you learned a lot of other things, we use different metric, okay? And once we are given a metric, we know a lot of things. The point is that the reality, the real application is this. We got data, we don't know the metric. That's why we need to learn the metrics. Okay? We need to learn whether it's Euclidean, whether it's the city block, the distance, we need to learn that metric. That's why you see our teaching, our subject getting more and more advanced. Why? Because we want to solve inverse problems. Give our a metric, for example, Euclidean. We immediately know from Hong Kong to Beijing, we know the distance. But what if they say the distance is 1,000 miles? Okay. And they say, okay, what is the metric I used to say it is 1,000 miles? Okay. So you need to find the metric. That is called inverse problem. So you see a lot of what you learned in different subject is all about inverse problems. All right. We need to find that. So here, I assume I know my metric. My metric across all through my lectures, I use Euclidean. Okay, Euclidean is the most simplest one. So that is this point is called a proximal point. Okay, you say projection is the proximal point. Okay, now I give you a general definition that applies to a lot of functions. Okay, assume you have a function g. This g function is convex. You want to give you a point x. All right. You want to find the minimal solution of this g function plus this quadratic function. Okay, remember, I always add a quadratic function. You think about this. If this 1.5, this is a coefficient. If that number is going to infinity, okay? If that number is going to, for example, is 10,000, 1 million, all right? If this number is too big, very big, you see the optimal value must, this optimal value must equal 0. Because if the point move away from 0, because the coefficient is so big, and suddenly this term is too big. So that's why it's called proximal, okay? So that is the half. So us want to solve this. Remember, this is a convex function. Add a quadratic function, it is strongly convex. Remember, I take away this part, it's still convex. So this function is half proximal, is strongly convex. I already said, is strongly convex. Okay? So I use the epigraph, here is closed. I always, for the definition to be absolutely correct, we needed this function to be proper and closed. So a function is closed. How do you say a function is closed? A function is closed is you use epigraph. So epigraph is closed. So for those who want to know that, you can look at this, but it's not my main point there. Okay. So this is what I just drew over there. The projection. If your function is an indicator function, so that is my C over there. So probably this side people cannot see it. What I draw there is this. So I have this function. I go this. Okay. I go. I cannot go. I have to go this one. Oh. So this is 90 degrees. This is the projection. And this is C. And according to my function definition of proximal, this part is indicator function. Okay. So I use dot delta C dot. This part is X. All right. That is the function. So you can see the proximal definition is really is a generalization of this projection to any function. So it's not just the delta. Okay, indicator function can be any g, any convex function. All right. If you want to know if C is the positive oscillant, okay, C is positive. The projection is positive part of your number. All right, you can verify this. It's very simple. You can see the. So people, or once again, I mentioned this. People ask me, sometimes my children don't like me explaining mathematics to them. Because they say, Daddy, you make things complicated. We want answer. You talk too much. Okay, you say too much. I always say, okay, why we need this symbol? Why we need this equation? Where is it come from? I can one line of that question. I can lecture them for 20 minutes. So that's why they didn't like me, my children. But they like the teachers, all right? Because the teachers always give this is the function, this is the question, this is the solution. That's all. So I don't think they. But anyway, my children's teachers are very afraid of me. Whenever I pop into the school, the teachers always afraid of me of commenting their teaching. All right, but I never comment their teaching. So anyway, so I like to say this. What seems difficult for all of us is that they want to generalize. Give me the projection, for example, give me the projection, okay? That's a natural thing. But the question is, how can you extend, how can you extend this projection to any function? Not just this C part, any function. You have to, this is a clever way to do that. Proximal, okay? Now, well, proximal, let's come to the very famous operator called a proximal soft thresholding operator. All right? What is the soft thresholding operator? It's just that G function is your absolute value function. Okay? Remember Lassau, we always have a target problem. Our target problem is a Lassau problem. Okay? It's a G function. If you substitute your G function to your definition of a proximal operator, the solution, you can write the solution. The solution is this. All right? This is a sine function. This is a component product. Okay? And this is the Marx function. We all know a Marx function because ReLU is a Marx function. Okay, so inside is the absolute function. Take away mu. Okay, so that is that soft thresholding operator is behind Lassau. Okay, don't ever underestimate such simple things. High school student can do this, okay? Can derive this formula. Remember, I said in my first lecture, we all know statistics is a big subject, all right? So many, 100,000 people working in statistics, in university alone, okay? Not to mention in industrial, in medicine, in drug companies, they all hire statisticians. But if you ask, if you ask, what is the single most significant contribution from statistics over the last 40 years, people would say Lassau. All right, look, the contribution is from here. You think it's simple. That's also bring to my point machine learning algorithm. Whenever machine learning algorithm is too complicated, it does not work. Okay, you have to be simple. Simple means everything. Meaning speed is fast, cost is low, and you see the meaningful result. So you can see this. Don't estimate this. The soft, what is a soft thresholding? So look, you might ask, okay, right, cannot be that simple, this formula. The point is this. We are dealing with very simple stuff. What about this axis matrix? All right? So that is why such questions keep people like me busy, all right, in the universities. So we all deal with the metrics, right? What about this matrix this vector is a matrix, and the matrix has some properties. What can you do about it? So that is that's also called thresholding, but its matrix thresholding is also very important contribution. It has applications in signal processing. Anyway, so this is a soft thresholding operator. What it does is the operation is very simple. So suppose you have a value mu equals 1. Within the -1 and 1, everything is 0. Okay, you put it 0. That is the thresholding. Okay, beyond this one is absolute value function. All right, so you can see such properties. If the mu is 1, mu can be any small number. Data mining. Feature selection. How can you select features? From 100 million features, you want to reduce it to 100, to reduce to handful 5 or 6 features. How? You have to set everything to be 0. How do you set everything to be 0? You cannot do it by your hand. You have to let the algorithm select it. The algorithm select any coefficient fall between this interval. In this interval, I set it 0. That is why it's called a selection. Okay, so data mining, I think you should have learned such things. It's okay. All right. You see, the proximal gradient descent is this. It's very simple. Remember, my first slide, ignore the proximal term. This is the proximal term I just defined. Ignore this term. It's just my gradient descent. It's my GD. So now, because you have a function f, g, remember my target today is f plus g. And with this g, I calculate the gradient for the good part. That is the f function. F function is smooth. Okay, it's differentiable. Then I update this point. Then I do proximal. Okay, I do the proximal. You see, the algorithm is so simple. All right. The point is that whether it works. All right, that is the point. Okay, so you can do this, and actually, this is the lasso, right? Algorithm. Okay, so it has a good interpretation. So this x plus k, this new point, actually is a minimization of this problem. This is by definition, by the proximal term. Okay, by the proximal term. And you can simplify, you drop the constant term. So in my lectures, all right, in my lectures, you have to remember this. If I want to minimize fx, minimize this function, okay? If it's equivalent to minimize fx plus fxk or plus any constant, okay? Because this is a number. Doesn't matter you minimize a function x squared plus 100, and the equivalent you minimize function take away 100. They are same. Okay. You are interested in the solution rather than objective function values. Okay, so what I wrote over there is this. You minimize a function is equivalent, is minimize this same function plus 100, okay, or minus 100, or minus, it doesn't matter, any number. So it does not change the solution, but it does change the objective function value. But we don't care about the objective function. We looking for the solutions. Does not change the solutions, okay? So my calculation, you see, I used the notation argument minimization. I talking about the argument of optimization. So what is the argument? The argument is the SK. Argument is X. All right. I'm focusing on X. This is my notation. I'm talking about argument. That's why I say equal, equal, equal. Actually, I dropped some constant term. Okay, I dropped constant term. Doesn't change my solution. Okay, you must remember this. Otherwise, you would get confused. You would say, oh, Professor G, everything you wrote here is wrong because they are not equal. Okay, the function value not equal, but the solution, the argument is the same, okay? Does not change the optimal solution. Look, that's my notation. Once again, I emphasize this. Argument minimization, okay? Argmin. So you can see that's why the meaning. So what important is this? Look, this is the formula. The meaning of the formula is in between, okay? Is here. Actually, you minimize a quadratic function plus gx, okay? So that is the important thing. Wow. So that framework, you can repeat. Probably you don't need to change any proof, any lines in my proof, first week proofs. And you just plug in the G, okay, proximal term. You can get this complexity, 1 over K. Okay, same thing. So for L smooth minimization, remember L smooth minimization last week, I talked about 1 over K. And this is same thing. So that's why I say the proof is similar to gradient descent and is left as an exercise. If you want, you can produce your own proof, but what I want to say is this. So after this, we take a break, okay? So I'm going to give you something new that significantly changes the convergence, okay? So what we do is this. We keep this proximal formula, all right? Remember the proximal gradient I just mentioned, we have this line, but there's one difference. The difference, this is previously this is xk, right? If you look at my previous slide, so the proximal formula, this gradient, is xk. But now, I don't do that. I do it with yk. So what is y? The y is xk plus something xk, x minus k. Actually, this is the combination of previous 2 points. So xk minus 1, xk. You produce a new point. So that yk is what I mentioned, puzzled many people. How could this one come out? All right? How could, after of nothing, you say, oh, you construct this yk. All right. There are so many ways to construct a new point. You produce this yk. And of course, this yk involves theta k. Theta k is a parameter, and theta k need to satisfy this condition. Okay. This was the 10 million renminbi. All right. Last year, Shanghai award that China, mainland China got a prize for mathematics, medicine, or something. So each got about 10 million, and this algorithm here is awarded 10 million renminbi. Okay, after tax, I asked the laureate, as Nestor, I will tell you, I asked him. He said he only got 7 million because of tax. Okay, because a lot of cost, he got 7 million, but it is good money, right? Anyway, so. Look, that is something. If you check on the ChatGPT or check online, you say Nestor acceleration. How Nestor find this one? Well, it is still puzzles everybody. But today I'm going to give you a proof that anybody can understand. It's just we don't know how this formula come up. Okay, so many people have tried to understand this. So what is this yk? This yk is this. Okay, this yk is this. Give me xk. I say this is xk. I use one index less. Give me two consecutive numbers x. So I do extrapolation. This is my extrapolation. So I got yk. From this yk, I do gradient step. Okay, so the point is this: how how do you find this yk? So that is a puzzling part. So okay, probably we take a few minutes break, then we return. Okay. Okay, let's continue. Uh, this is celebrated, this well-known, now become very famous algorithm, only 2 lines, all right? Only 2 lines, simple to implement, and it is fast. So I like to say this theta k, the choice of theta k, we have many choices, all right? The point is this. The point is the theta k has to be in the order of 1 over k. All right? That means your step length is like 1 over k. So this 1 over k, I mentioned it many times, 1 over k. Why the step length, okay, is 1 over k. It's like, it's in the order of 1 over k. So this number, you look at this number, is 1 half and 1/3, 1/4, 1/5, and go forever, right? And this step length is going to be 0, okay, when the k is big, all right? And you might worry. So that's what I thought when I learned such things in, not this, I learned the algorithm when I was in the, actually doing the, my PhD. So at that time, I learned optimal control. That is annealing. Okay, probably you learned some simulation. So the step length is always going to 0. I worry that If you goes to 0, that means you don't change, right? It's so small. How can you change? So that is puzzled me a lot. Years later, I realized that, okay, each number is small, right? But if you add them together, we all know that is a harmonic sequence. And this sum going to infinity. All right? So 1 over k, this step length, don't underestimate. Don't say, okay, it's very small. It does not take you, well, actually, you can observe in future when we talk about nonlinear functions, non-convex functions, we see the algorithm going zigzagging, cannot move. All right, that means your algorithm, your step length is too small, and sometimes we need to get out of it. Okay, because this is too small. Of course, accumulation going to infinity, but you cannot wait for infinity, right? You cannot go until years later you want to get your result. You want to get your result now. So that is the strategy that is called restart. Okay, in machine learning algorithms, you always say there is a mechanism ask you to restart. How many steps you restart? Probably you say, okay, every 100 steps a restart. What is restart? Restart, you reset your step length. Okay, so among other things. So I just like to mention to you that this theta got many choices, but the magnitude is like 1 over k. Okay. All right. So that is the famous claim. The claim is this. Remember this, our capital F function is f plus g. Okay, there are two functions. So current iterate, the function value to the optimal value, the error, this is always positive, right? Because this is the smallest value. Any value is bigger than that one. So this is positive. The positive, the difference is always below this one. It's always the initial distance. Okay. Once you select where you start, okay, this is fixed. Okay. So this is the L that is your function L smooth, and this is theta k minus 1 squared. Remember, theta k is the order of 1 over k. So the right-hand side is about 1 over k squared. Okay, you think about this. It's really fast. Okay, 1 over k squared. And so this is what we said is already here. 1 theta k is 1 over k. You get the 1 over k squared complexity. That is the original claim. Okay, by Yuri Nesterov. I'm going to show you that. So the result is simple, but the proof is very difficult. Okay, what amazing part is this? Majority of the proof is simple. Okay, it's just one step is difficult. All right, so how simple it is. This is a straightforward application of the convex function or definition of a proximal term. You can do it line by line. So once again, I dropped the constant term. So I define this whole thing as a Kasai function. Okay, this Greek letter. I use that. And remember, this is a strongly convex function. And this sk plus 1 is the optimal of the strongly convex function. Remember, we have a quadratic growth lemma. The quadratic growth, I apply the quadratic growth result to this quadratic function. I got this formula. I got this bound, the bound in 5. That is, that is look. for student, actually for me, when I first learned something, I thought that all right, this is not that difficult if you know the gradient descent GD and you know we can get this, all right. Um, After you get the proximal, okay. You use the proximal because the proximal you get a quadratic term. Quadratic term is is strongly convex function. Okay, so you can see the step one is an inequality on the proximal step. This part, um, you can have a look. Is not difficult. Okay, now the bound on the function value, we want to, when we minimize the function, we want to bound it. Okay, so the bound function is also straightforward. Okay, but something strange come out because you are dealing with a new algorithm that is what we call accelerated. So by descent lemma, that means the function is L smooth, right? L smooth, you can use descent lemma to do this, and this part it happens to be the previous function, theta function, what we already defined. Okay, you can put this, and then you apply the bound in 5, the previous slide, you get this one. So from this, all right, this is f is a convex function. You use the definition of a convex function. This is less than fy. All right. Remember, f convex function is above is tangent line. All right. So then you have this. Finally, you get this xk, but you have a yk, xk. All right. Previously, this is all xk. If you look at the GD, but now it's all is yk and xk mixed. All right. And remember the popular technique is that you add them together, they cancel each other. But now you cannot cancel each other. All right, because the positive part involve yk, the negative part involve xk plus 1. Okay, that's why so this part, that's why I ask you to look at the proofs, look at my slides before coming to this lecture. The reason is that really it's blackboard things. Initially in the past we always demonstrate on the big blackboard. Okay, so that's why we always at my Peking University, the mathematical or data science class, lecture rooms, they all have big blackboard. Okay, you can push it up, pull down, and you write a lot of things. The university want to replace with smart screens. But the faculty of mathematical science, Peking University, all said no, we don't need that. We need a blackboard. All right. So initially we need to demonstrate on the blackboard line by line. But now you can read this. The detail is, as I said, is not that difficult. We know this, okay, because we learn GD first. Then we know such quantity. We know such bound. But now, this, as I said, the strange thing is this: yk, xk plus 1, there's no way you can cancel each other in order to have a bound. Remember, because it's iterative, you want to cancel the middle steps, okay? Therefore, you got 1 or 2 terms in the end because you cancel each other, right? So that is, you remember, I always, sometimes I show my children why factorization, why cancel each other is so important. Remember, in our school days, we always ask to calculate such quantities, right? Do you still remember in our school days? Right? So what do? You cancel it. So this one is like 1 over 2 minus 1 over 3, right? This is the 1 minus 1 over 2, right? So in the middle, you cancel every terms. In the end, you only got the initial term and the last term. So that's the trick. And if you relate that trick, it's just like that. It's just appearance is different. Look, if this x, k, x, x, if you add them together, they cancel each other. All right? So that is a trivial technique that we already acquired in our high school days. It's just it's just the component is the building block. What I refer to the building block is complex. It's more complex. It's not like a single numbers like this. Okay, so if you think that way, it's not that hard. Then probably the step 3, you simplify because you have yk, xk plus 1, such things, you simplify it. What you simplify it is that you construct a new point y, you interpolate. So this is a convex combination with the optimal solution xk. So you do that, you substitute the y, because remember the previous slide you got y, you substitute it, you simplify, then you get this. Okay? Remember, if you said, okay, this does not, I don't care about this. Remember, this is 10 million renminbi price. Okay? A few lines, you get 10 million renminbi. All right? Think about, how much we earn after we graduate. Okay, so that is a significant amount of money. So you get such a simplification. Look, now this is the most difficult part actually. This is a magic step. So step 1, 2, 3. Okay, step 1, 2, 3. I'm pretty sure anyone in this room, if you studied GD, gradient descent, as your subject, for example, you do it with your PhD in optimization, you use GD often, you derive the bound by yourself because it's a textbook. GD is already in textbook. And 1, 2, 3, I'm pretty sure anybody can do it. All right? It's just that accelerated version, that theta k, how they come up with this. Okay, this is step 4. All right, this is a magic step. Still, I don't know how the this part, and everybody asked Yuri Nesterov, how did you come up with this? All right. And his Euro answer is, I don't know. And so he did this. So because you have YK, right? He combined with XK again. But with this strange 1 over theta k. All right. So if they do this, okay, you simplify, okay, you substitute yk because you already construct yk, you substitute it, so it come up with this, okay, come up with this part. All right, the power of this representation is showing, is reflected in the below, in the following. Okay, you substitute this theta, okay, so to the previous step 3, then you can see this is the function. All right, you can see the last terms, x star zk, x star zk plus 1, and this is minus. The coefficients are same. All right, that means if you add them together, they cancel each other. In the middle term, it's like just like this. In the middle term, you cancel everybody. Okay, so you only have the initial point and the last one. Okay, this part log I copied. All right, still now is beyond my comprehension. It's beyond anyway. this accelerated algorithm is a done deal. You cannot improve. Okay, anybody who want to improve, you will see my last slide. Okay, my last slides will tell you you cannot improve. Okay, if you want to improve, you work on particular functions. You cannot say, okay, it's L smooth. Okay, L smooth assumption is very general. So this is the part. This is the whole part. This is the central part of the proof. Is this you get the two terms next to each other. One is positive, one is negative. If you add them together, because it's iterative, you add them together over the k, you cancel each other. In the between, you cancel everybody, and you only get the initial and the last part. That is what we have here. So you can see you rearranging the terms. You see, this term is really nice now. The k plus 1, the next iterate, previous iterate, you have a fraction y minus theta k. Remember, theta k is below 1, is 1 over k, all right? And these two parts, they cancel each other. And well, still is not that simple, because if you do that, you would have 1 theta k. All right, this is annoying because theta k is changing. You would have many factors: 1 minus over 1 over 2, 1 minus 1 over 3, 1 minus over 4. So what they do is that they divide by this. They multiply this one, divide by this one. That's why initially that the condition come from. You multiply this, all right, and then you substitute, right? You got this, you substitute, you just substitute. Then you get this, all right? Then you add them together because it's what is that called? Telescoping technique. What is the telescope? Telescope, you can say, you can push it out, you can pull it in, all right? It's like a telescope. So it's like, because this k, from this you can k minus 1, you can push it out. And in the between, they all cancel each other. Then in the end, you got just one term, okay? Then you divide by this term, you get your claim. So, you can look up in the internet. I don't think anybody's proof is simpler than this. All right. As I said, there are many proofs. All right. In mathematics, there's a journal called SIME Review. SIME Review, that is the Society of Industrial and Applied Mathematics. Okay. It's industrial and applied mathematics. And review, this journal is probably one of the best. A journal only publish influential papers. I noticed there's one paper from physics. Okay, they use physics to explain this algorithm. Okay, so you can see different area, different people have different opinion, different way to interpret this algorithm. It's fascinating that it has so many meanings and different areas that have a different way. So they use, for example, dynamic system to explain this. So, look, I won't, I won't test you a proof like this. All right, it's too complicated. As I said, the part step 4, I don't understand it. I copied it. So it's just very technical there. But the point is that if you do that, nowadays, that step is called momentum. Okay? Probably when you read machine learning papers, deep neural network, you bump into the term momentum. Okay? That momentum is called Nesterov momentum. Okay? So it's all come from him. Of course, momentum is being used by other people, but it's just momentum as acceleration. So what it says is this: if you do the GD xk minus 2, xk minus 1, xk plus 1, if you do that, all right, it is fine. Okay, it converges over, the complex is 1 over k. But now is this: every point you find a nearby point. Okay, the nearby point is just boost you going faster. Okay, so give you extra energy to go faster. Okay, so that is one that is the point that how you find it. Okay, so that is look, this is simple, but the demonstration is simple, but the point is that how do you find that y? Okay, so that one. If you, that is for the point, the iterate, the perspective. If you look at the function value, okay, if you look at the function value, the function value is this. This is the quadratic function. Once again, you might do it. You might ask ChatGPT. You say, "Okay, please demonstrate Nestor's, accelerated gradient method to me," and that will give you this. This is plotted by ChatGPT. Okay, so initially you get this one. So this is the 2 points. You get x previous. Remember, you always use previous 2 points. Okay. Gradient method, remember. So this is a very important point. I go to the initial one. Gradient GD, you only use previous point. Okay, you only use the information. You assume all the information is in the previous point. You think about the Markov chain. You learn the Markov chain. Markov chain is the current point is does not matter. The next one only depends on the previous point. And all the previous steps, you forget about it. That's called Markov property. So the GD is just like that. I only rely on the previous point. But the acceleration version depends on 2 points, xk minus 1. All right? They use 2 points. Okay? So you see this this is the objective function value. So you use this 2 point, and GD you would get this one. Okay, but from GD you accelerate, you get this one. Okay, you push a little bit further. Okay, and a little bit further, and from that point you do it again. So accumulation is that you get a fast the convergence. I believe if you search, I encourage you to search. I think somebody has produced the dynamic like a movie. You can see how points change. But anyway, this is for people who like codings. They do such things. Well, that comes engineering science people. Initially, they don't know what is Nestor's algorithm. Okay, they don't know this. They know this. They know Fista. Okay, so Fista is this is one. ISTA is called iterative soft thresholding algorithm. Remember at the beginning I talked about the soft thresholding, very simple formula, right? So this algorithm is for Lasso, is for G, is for the absolute value function. Okay, L1. If you do that, and if you apply the accelerated version to this one particular application, you would have this formula, and this formula is different from on appearance is different from the what we previously learned. This time I use TK rather than theta k. There's a close relationship between TK and theta k. Okay? And this algorithm is called FISTA, okay? Because it's accelerated. Initially, they use this. This is GD. They call it ISTA, iterative soft thresholding. That means you always cut some point, put some point 0, 0, 0, and in the end, you got the right answer, okay? So they say, okay, you can accelerate it. This is what called FISTA. And this one is very famous for image processing. I mentioned that denoising in image processing is very important. I mentioned that every day we took photos with our mobile phone. The mobile phone is your hand is shaking, or the light is not bright, is dim, and because the surroundings, we all know that the signal processing is especially photos is depends on the photons. You know the the atoms. All right, when you have a light, is reflect on your camera. There's there's built-in things, and that number of photons that electronics is random. All right, depends on how bright your light is, depends on your surroundings, depending on, for example, temperature, and that's why same thing, different people take different photos. All right, but you need to reduce that noise. Okay, this algorithm is used there. Okay, very fast to denoise, to remove the noise very fast. It's you cannot just realize that what you took, the photo, is already being computer processed. Okay, it's very fast. Okay. All right. So if you want to see how these things works, all right, you might have an example to show this. So so I encourage you to work through by yourself. Why? Probably in your exam, I would give questions like this for something for you to calculate, right? So what I have is this: is a typical Lasso problem. You got only two variables, x1, x2. This is the quadratic function. There's the f part. F part, remember, is the quadratic function. You add the quadratic function. That's a linear term, right? We got a linear term, we got quadratic term. So this is the absolute value function. This is the L1 term. So I use FISTA to calculate the first two iterate. So I know L equals 2. I leave it to you y L equals 2. So it's L smooth, this function. It's L smooth, it's quadratic, y L equals 2. So I calculate the gradient. Look, the quadratic function gradient is very easy to calculate. You start from y1, x0, 0, 0. You start from origin. You calculate this is the update, this is the GD. Okay, this is GD. You calculate this. Okay, then you do the soft thresholding part. The second one, soft thresholding part. That is the x1, and the column here, 1 come from the sign of this. Look, they are all positive. That's why the sign is positive, positive 1, positive 1. Okay, if one of them is negative, this the sign is -1. Okay, so you this is the max operator. You do this. There's the first x1 is half 0. Okay, then you calculate T2. Though we have formulas, remember. So we have formulas. You can calculate this. So you can calculate y2, okay? You substitute to this, and then you calculate U2. That is the U2 part. This is the gradient. This is the gradient step. Forget about the G part. That is the absolute value function part. That is GD. From GD, you do G part. That is the proximal term. You get this, right? So as I said, you should you should calculate by yourself, okay? By doing that, okay? So I emphasize in tutorial class, usually tutorial class, the problems probably is slightly more difficult, more challenging than you would see in your exam questions. Okay, that's why I said if you do your tutorial problems, every time we have 6 questions, and you should expect that the exam questions is not more difficult than those questions. They may have 1 or 2 small questions that you may not think, but that is my, as I said, I don't want to put anybody in trouble. I want you to learn something, and then you tell people, all right, this algorithm converge. We learned in class. We know it's proof. And that's all. I don't want you to reproduce the proof because I cannot reproduce the proof myself. Why would I ask you to reproduce the proofs? But the point is that we learn, we know, all right, we can say in confidence that it is true. So for numerical part, please use your own hand. I did it by myself. I calculated by my own hand. I didn't use my, I could code it. All right, I could use a symbolic computing to do it, but I didn't because it's so simple. You can do it in a minute. Okay. Okay. Right. So I mentioned Lasso. Okay. So Lasso is a quadratic function, right? It's a quadratic function. It's the small question is just the the simple example of the Lasso. All right. Then the point is that what is the L, right? So we need L smooth. We need that L, that quantity, right? We need this quantity L. We need to estimate. We need to estimate this L. Okay? How do you do that? So Lasso is doing this. Because Lasso is a quadratic function, you can calculate its gradient. The gradient is like this. Okay? Quadratic function, you need to know how to calculate its gradient. All right? Mark my word here. You will see something like this quadratic function. Okay? And you calculate the gradient. And what is this? This is the largest eigenvalue. Okay? This is the largest eigenvalue. So for a matrix multiply a vector, if you calculate its Euclidean norm, this L2 norm, it can be bounded by the largest eigenvalue multiply the change of the variable x and y. Okay? So you can see this bound is very important. This bound, left-hand side is a matrix multiply a vector. Right-hand side, they're separated. 2 quantities. One quantity is on matrix. The other quantity is on difference x and y. Okay? So, and this is your L. Right? You can test. You can randomly generalize this matrix A. All right? If matrix A is only by 50 by 50 matrix, it's not big, it's 50 by 50. And this number could be 1,000. Okay? Think about in our real example, real data, we get millions of data point. So that means the matrix A transpose times A is about millions times millions. And this eigenvalue, the largest eigenvalue, could be 100 million. Okay? And remember our step lines, there's L, 1 over L. If L is 100 million, so that number is very small. So that is why in real implications, so machine learning algorithm, you may see, they don't use L. They use adaptive schemes. Okay? They estimate L. Okay? They don't use this big one. Look, this is less than or equal. Does not mean this L you have to be. This is just the upper bound for L. That's the upper bound. You need to get a more accurate one. So that is why you need to admire those engineers. Engineers, what are the engineers? Engineers make things work. Whenever you put a put a task to engineers, okay, I make it work. Okay, that's what they do. That's what they are good at. So theoretically we have a accelerated algorithm. It's not all. You have to do this. You have to use a smart way to estimate L. And if you want to learn more, you can download the Python program coding or anywhere, and you see how they choose L. Okay, for many small implementations, they simply use this. Okay, you can see they simply use this. The Python program simply uses this number. But for real applications, you have to use dynamic things to do that. All right. Okay, so that is so I used so don't is not very big. It's 100. It's only 100 times 100 the transpose, and you can see that blue part that is east. That is the bottom line is the Fista, and you can see the thing is that the Fista reduce the function really fast. Okay, at the initial point, eventually they become flat. Okay, you may wonder why this part going to flat. This is a typical performance. You may wonder why, because you only used gradient information. If you want to decrease very fast, you have to use second order information. So that is Newton's method. So somehow, down the weeks, I'm going to talk about Newton's method. That means even faster than this. Okay, but the cost is that you have to use second order information. At the moment, we use gradient. That is called first order information. Okay, that's the terminology that widely used. If you use gradient, is called first order. Okay, so that come to the last part of my lecture. I talk about the comment for the development of this algorithm. So Yuri Nesterov, you can Google him. Yuri Nesterov, he published this algorithm in 1983. 6 pages, okay, in a Russian journal, okay. That's why Western people don't know. So we all know because well, you are too young. The 1990 is the former Soviet Union, Soviet Union dismantled, okay. That time, 1990s is the most difficult time for people, Chinese people working in America, because they couldn't find a job. There are so many Russian mathematicians left the Soviet Union and went to American and USA, went to Europe. And Nesterov went to Europe, okay? he found a job in a small university, maybe not a small university, yes, university. He stayed there, and so in after that, so this now become very famous. At that time, he didn't know. He said, "That's no use. 6 pages. Nobody care about this." So he did. He moved on to the interior point method, but I'm not going to talk about the interior point method in my course. So, uh, he want to do something new. So until this FISTA thing, the machine learning people and what they call rediscovered. Okay, so back and Tabor 2008, the FISTA paper, the proximal gradient version, and that was controversial. And because this paper, FISTA, becomes so famous, so popular, one society want to give a prize, a bigger prize to this one, but people are against it, saying that the original idea was not from them. All right. So anyway, so what we used is this Chinese guy, Zheng Po Cheng, and 2008. He gave that proof. Okay, that proof probably I claimed probably is the most the simplest proof of the result. It's not from Nestorov, it's from Po Cheng, and this one is also he was genius because he died. But we shouldn't say he died. He vanished. Okay, his genius mathematician, his technician, and people once said that if you have something to prove, if you cannot do, give it to person, give it to the thing. He can do it. All right, that proof. I believe many people used his proof, used what I used this. But anyway, now Nestorov every year visit applied math, visit us, and now he most I think 50% of the time he stay in Shenzhen. Okay, uh, uh, he's a very nice guy. Uh, uh, Particularly like Chinese wine. Okay, Motel he can drink a bottle. Okay, so he's a mathematician. Um, okay, let me summarize. So our target is this. Our target is for the Lasso problem. Okay, for the Lasso. So this type, we have a structure. So f function plus g function. You think f function is a very nice function. G function is L1 function, right? Uh, so it's absolute value function. And proximal gradient is like this, right? You without this part, without g, this is GD. With G, you only need to calculate the gradient, calculate the proximal. Remember, with the absolute value function, we have a soft thresholding operator. Okay, so you have a formula. Look, I used proxy, but it has a formula behind it. But APGI, remember, is accelerated proximal gradient algorithm. I didn't say accelerated proximal gradient descent. I didn't use D. I used A. The reason is that this algorithm is not decreasing every time. Okay, the trend is decreasing very fast, but sometimes it's going up, going down, up. It's like this. Okay, so we call it accelerated proximal gradient algorithm. So it has this formula. So the amusing part, this is the first one, how you construct YK. All right, that's something I don't think anybody, a random person can do it. But we know this part is very well, but this part a little bit magical there. But anyway, it's become celebrated that. So the consequence is this. The consequence you become from 1 over k complexity to 1 over k squared complexity. And the price is this. The function value is not decreasing. Every time it's not decreasing. It's decreasing in the trend, okay? But sometimes it's going up. Most of the time it's going down. But sometimes it's going up in order to accelerate, okay? So you can say the PGD, your function value is always decreasing, okay? As I said that now, previously you use 100 steps, now you use 10,000 steps. Previously you use 10,000 steps, now you only use 100 steps. Okay, so that is the steps that you can reduce. Okay, so the hard part is this: what is L? How can you calculate L? That L is uh, often is dynamically chosen. Okay, I finish this lecture by saying that 1 over k squared you cannot improve. Okay, because you might say, okay, look, 1 over k squared you can get a 1 million, 10 million renminbi price. How about I increase 1 over k cubic? Okay, the bigger the better, right? There are people doing that, but you have to assume something else. So the Nesterov also give an example saying this. If you only, any algorithm, we talk about any algorithm, if you only use gradient information, that is the first order information. If you only use gradient, okay? And the purpose is to find the gradient equals 0, okay? You always, your next iterate is always spanned by the gradient information, all right? By the gradient, this is span, this is space, okay? So he can always construct a function that give any x, k, the error, remember our bound is less than or equal 1 over k. Now he said must be bigger than 1 over k squared. Okay, that means 1 over k squared is optimal. You cannot improve. Okay, if you want to improve, you have to assume something else. Either you assume your function is very special, or you use information beyond the gradient. Okay, so the assumption is that you use gradient information only. Okay, in future we will see the second derivative is very important. Remember, in our calculus, we learn gradient. We also learn second derivative. We rarely use third derivative. Okay, but now the optimization method advances so much. Third derivatives, people also use third derivatives. Okay, but it's too complicated. It's only for special problems. For us, first order information and the second order information is enough for us. Even for machine learning algorithms, second order information nowadays is used to explain why, for example, Adam is so efficient, is performance is so good. They use second order information to explain it, but the algorithm does not use second order information. But there are research that are probably, when I talk about the second order, second derivative, I may talk about the atom they widely used in machine learning. Use the training for the deep neural network. Why second order information helps is performance. I think that is so that is what I want to talk about today. So the next hour is for a tutorial. All right. Uh, you may you may take a break. Okay. So before we finish, any questions? So you can always ask me questions. You know, it's a two-way communication. It's not just I blah blah blah. I talk about. I can talk about such things forever because I'm very familiar with such things. All right, but I have to be selective if you want. To say, Professor G, reduce your coverage. Okay, I may give you more example rather than but we only have one result, one proof. Okay, we cannot reduce anymore for such things. But if you have any comment, any requirement, anything want me to change or you just let me know. Okay, you can also interrupt me anytime. Okay.